And we'll go on to the next talk, which is also about pandemic scheduling. And so this is physician scheduling during a pandemic. And Lucas Kletzander will be giving the talk live from Vienna. Feels like Eurovision here.
Okay, so hello and welcome to my talk. This is joint work together with several colleagues from the Technical University here at Vienna and together with Matthias Krainz from St. Anna's Children's Hospital in Vienna. So basically, when the first wave of the pandemic hit, all of us pretty much had major disruptions in our work life. And for us, one of the implications was that we couldn't go to conferences in person, and usually we had to work from home. For a hospital, the problem is they can't work from home, and obviously they still have to keep their all their patients supplied as well. So we were actually approached by St. Anna's Children's Hospital during the first wave in order to help them deal with the pandemic situation at their hospital. So a brief introduction to the setting. Basically, that's not St. Anna's Children's Hospital, but the basic structure is that we have a hospital ward, and in this hospital ward we have several departments. And basically, for example, one of those departments could be oncology, and then within this department we have several stations, for example, surgical oncology or medical oncology in this case. And so in general, stations are somewhat separated in their location, and each station needs to be staffed with certain doctors. And what we now want to achieve in this pandemic scenario is that doctors do not switch between stations very often, because then that greatly increases the transmission risk. And also if one of them needs to go into quarantine, then basically multiple stations might be affected and a lot more colleagues might have to go into quarantine as well. So there's two major objectives in our work: basically minimize the number of station changes and also keep some stuff in reserve in case there are still some sick cases and some quarantine cases. So let's look at the structure of the requirements for our problem. Basically, the requirements are defined per station, day, and required skill. And in the table to the left, we can see such demand for just one department and one day. So we have 3 stations here, S1, S2, and S3. And also we've got something that we call a common station, which is basically work that needs to be done over the whole department that simply cannot be assigned to an individual station. And in this case, we've got 3 different skill requirements: senior physician, physician, and assistant physician. And each of them needs to be covered with a certain number of doctors. And on the right, we can see basically an assignment of 5 physicians to those 5 positions that are required here for the regular day shift from 8 to 4 p.m. in this case. However, there is also demand for an additional night shift. So basically one of those physicians needs to stay overnight for on-call duty basically, and needs to extend their own shift. That's what we call subsumed demands, because this shift actually subsumes one of the regular day shifts, but it can be from multiple different skills and multiple different stations. So in this case, one physician from either station 1, 2, or 3, and from either skill, senior physician or physician, needs to stay for the rest of the night. And in this case, physician 4 is chosen. Now, the general scheduling constraint in this hospital setting, even before the pandemic, would be the following. We want to have 1 shift per day according to the physician qualifications. So there's actually a preference matrix where some assignments are simply not possible and others have different preferences that might also encode how well a physician is trained to work on a certain station. Then there's a requirement for the maximum number of consecutive working days. There are some forbidden sequences of shifts. Obviously, after a 24-hour shift, you probably wouldn't want to start the next day shift immediately. There's a maximum number of weekly working hours, and there are certain fixed days off for individual physicians. And the original objective would basically be to minimize this preference score. So for each physician, there's a preference for each combination of station and skill. In the pandemic context, we've got several new constraints that are added to the problem. One of them is that we do not want any department changes because that would increase the transmission risk. And then there are 3 more soft constraints that are added to the problem. So the first one is that we want to reduce the number of working physicians during the period. So some physicians should actually stay in a reserve at home, basically, and then they can come to work if there are any sick leaves or quarantine leaves. Next, we want to optimize the risk group assignments. So some doctors might actually also be at risk of getting COVID. And so they should work in stations with lower transmission risk. For example, where there are only pre-scheduled patients that are tested previously combined to rather than emergency patients that might be untested. And the most important objective is to minimize those station changes to reduce the transmission risk. So related literature, there are also some other works due to the pandemic setting. In the medical scheduling area, basically, there's some work, for example, in nurse rostering and also some general personal scheduling work. Just in the previous talk, we've heard school timetabling applications. But basically, our work deals with the physician scheduling setting, which has some specific demands, constraints, and assignment constraints, and also this department and station structure. And we're introducing several novel pandemic-related constraints and objectives in this setting. And what we did is we formulated this problem as a CPE problem, and then did an empirical evaluation on real-life data from the hospital with several different solvers and different configurations. So let's look a bit more at the CPE modeling. So basically, our input parameters are the following. We've got a scheduling horizon that was typically 2 weeks in our problem. We've got a set of departments, a set of stations where each of them is assigned to precisely one department. We've got this set of common stations that covers the work for the whole department. We've got a set of physicians to schedule, a set of skills, a set of high-risk physicians, which is a subset of the total set of physicians, and then a set of shifts. And now the decision variables are 3 sets of variables, where basically for each physician and each day, we have to assign 3 things: the shift that they're assigned, the skill that they are assigned, and the station that they're assigned. If they have a day off, then all these 3 variables are 0. Otherwise, all 3 of them have to be non-zero. Now, probably one of the more complex constraints in this problem is how to deal with the cover requirements. On the top, we can see the regular cover requirements, basically for regular shifts. And what they say is essentially, if we sum up over all the physicians that are assigned a particular shift T at a particular station S and a particular skill assignment K, then this needs to be equal to the demand for this particular combination for each day. Now, there's also this problem to deal with the subsumed demands. So basically, either this regular day shift, shift type 1, or the extended 24-hour shift, shift type 2, basically covers for the regular day shift, because this extended shift is really just an extension to a normal day shift. And then for these extended shifts, we've got a different demand constraint, which basically says that's in the bottom line, which basically says that these 24-hour shifts need to be covered by an assignment to any station of the corresponding department and any skill in the required skill set. So that's always over multiple stations and multiple skills to cover this special requirement. The other constraints are now a bit easier. There have to be at most 6 working days in a sequence. So at least 1 out of 7 needs to be a day off. The department changes are modeled as basically every physician is assigned to the day off department 0, and there can be at most one other. That's now how we deal with the soft constraints. So basically the number of working physicians is the first objective, is simply the sum of all physicians that have at least one shift assignment. The preference score is simply summing up over all the preference scores for each physician and each assigned combination of station and skill. And also the highest preference value basically is not allowed, because that means that this combination is simply not possible. Then we sum up the risk penalties, where for each physician who is at risk, so in the set R, we sum up a certain risk value depending on the departments they're assigned. And the number of station changes is counted as basically as soon as the previously assigned station, so that's what LS stands for, as soon as the previously assigned station was not 0, so there was a previous assignment, and it now changes from one day to the other, we basically count this as one station change. Now the objective is then a linear combination of all those values, and the weights actually have been determined by the hospital staff. So we can clearly see that in the pandemic scenario, the highest weight has been put on the number of station changes, and well, the preferences would be nice to fulfill, but if it's not possible, the transmission risk is more important. But we will see a bit later that actually we still have very good results regarding the preferences. So let's look at our results. So we mainly evaluated one real-life instance that we got directly from the St. Anna's Children's Hospital, which includes a 4-week scheduling horizon for 2 departments, where each of them has 3 different stations, plus this one common station, and in total 26 physicians that were needed to be scheduled during the first wave of the pandemic in April 2020. And we also wanted to evaluate our approach in different configurations. So we also looked at 3 different search strategies and 4 different redundant constraint configurations. We modeled the problem in Minisync and then used various different solvers, both MIP and CPE solvers, to actually solve the problem with a time limit of 1 hour. So when we compare the results from the solvers, we can clearly see that this particular problem was way better suited for the MIP solvers compared to the CPE solvers. And if you think about it, that kind of makes sense. We've got a lot of soft constraints that we combine. So actually, Chuft and G-code have a hard time even finding feasible solutions. The best solver in the CP direction basically was WAR tools, where we got 10 feasible solutions, and 8 out of the configurations produced our optimal solution. The MIP solvers both produced the optimal solution in all configurations, but only Gorobi was able to prove optimality in 9 of those configurations. We also looked at a larger instance, which is basically double the size and also double the number of physicians then, where Gorobi actually found the same solution in all 12 configurations, but couldn't prove it to be optimal. And Cplex found a feasible solution in 11 configurations and 9 with this best found solution. We did not really see a clear picture regarding the search annotations and the sets of redundant constraints, so there was not really a significant winner in this direction. Now, what we also looked at is actually the impact of the pandemic-related constraints. So what we did is we actually removed the additional pandemic objectives and just computed the solution for the preference scores. And basically then afterwards evaluate the additional objectives as well. And what we could see is that actually in our full model, we just have 1 station change in the 2 weeks. While if you just don't care about it in the optimization, then the solver would change the station 69 times in this example. However, while still finding an optimal solution with the same preference score. Also with 2 more working physicians, so we could actually fulfill all the demands while still keeping 2 physicians in reserve. The risk group assignments were the same, but basically the main message here was that we can reduce this number of station changes without actually reducing the preference assignments of the physicians. So basically, to sum up, we've introduced a novel pandemic-related physician scheduling problem where we worked on a real-life instance from St. Anna's Hospital. And just as we feel in the previous talk, there was only a very short time frame to produce solutions. And even during this time frame, the requirements repeatedly changed. So we actually used constraint programming, which was very helpful to rapidly encode the model and also exchange individual constraints easily if that would be necessary. So as future work, we might also extend this approach to related problems in other medical settings or even outside of the medical domain. Thank you very much.
All right, thank you very much. Are there any questions? So I see, oh, there's a question from Roland.
I was just wondering, there's a considerable work on, hospital scheduling, rostering, whatever. So I understand that, maybe you have this time constraint to get the solution out quickly. Not CPU time, but, just to deliver the thing quickly. But how does the problem really differ from all those existing works?
Well, we've basically dealt with a kind of specific demand structure that they had, and then included these additional objectives to really reduce the number of contacts in this setting.
Right, but probably those constraints could also be there in existing work, right?
So
or you could just add those constraints there, right?
So I'm not aware of this particular setting of constraints in the literature so far, but maybe there are some related works.
Okay, I don't know it well enough. I'm just wondering.
Are there any other questions? Is there a question in
There's one
Vienna?
in Vienna.
Okay, go ahead.
Give me a second, please.
Thank you for your talk, Lucas. The contrast between MIP solver performance and CP solver was really evident. And I'm progressively persuaded of the fact that when it comes to a use case scenario, there's no best solver, but it's a use case choice. What are your speculations? Can you explain further why you think that this problem specifically is more probably best solved by MIP than CP, and which part of the formulation makes it compatible from?
Yeah, so at least in my experience, it is often the case that the CP solvers are very good if there are lots of hard constraints that restrict the feasible space, and then you can still have some soft constraints to optimize in there. While when there's a lot of feasible solutions, but most of them are terrible, and you have a complex combination of soft constraints to optimize, then in my experience, at least, the MIP solvers perform much better. And the nice thing actually about this modeling approach in Minisync is that you can just model your problem and then choose later which solver you're going to continue with. So that's actually very nice if you have time pressure or in general want to experiment with the different approaches.
Thank you.
Did you use parallelism for CPSAT?
Sorry?
Did you use parallelism for CPSAT?
I'm not sure which parallelization settings we used. Right
So
now.
I think we did not. So
Yeah, because
they-
performance
No,
is
we did not.
way better with
So
parallelism.
we
We
should
did not.
have labeled it.
Yeah.
This was all single threaded, yes.
Yeah, it's really different.
All right, thank you very much. I think we're going to move on to the next talk.